Alright, welcome back to the final review. There will only be one more lecture this week. I'll just combine them together, and then you can use any extra time that you might have to study some more, to study extra. So let's continue with the final review. Our next topic is counting. So this is stuff closer to the end of the semester that that's all more recent. So let's talk about that. So the first thing that we started with when we learned about counting were the product and sum rules. You thought of it in terms of like we have a set of A things, like things in set A that we could do, and things in set B that we could do. Maybe there's 2 things in set A and 3 things in set B. The product rule says that if there are A ways of doing one thing, like it's 2 ways maybe, and there are B ways of doing another thing, maybe 3, then there are A times B ways of doing both. And that kind of falls out. It's like, if I have to do one thing from A and one thing from B, what are my choices? How many options do I have? Well, I could choose this thing and then this thing, or that first thing and then this thing, or that first thing and then that thing. That's 3 options, and then of course you have another 3 if you choose that one first. So there's a multiplication happening. It's A times B ways of doing one from each. The sum rule says something, again, very similar. It's if you have A ways of doing one thing and B ways of doing another thing, and you can't do both at the same time, there's no overlap, then if you just want to choose something to do from the entire set of everything, from the whole universe, then, I mean, you have these 2 things over here that you could do, or these other 3 things that you could do, so you have 5 options total, right? There are A plus B ways to choose something out of everybody. That's like a union. And this is kind of like a, what's the right word? This is kind of like a Cartesian product. So that's where it all comes from. Next, we talked about permutations. And so a permutation is just a way of ordering a set of something. So maybe I have a set of numbers. We can talk about all the different permutations of this set of numbers. If I have 4 numbers and I'd like to permute all 4 of them, I want to compute every possible permutation of all 4 of those numbers. Every permutation is a tuple. 1, 2, 3, 4. It's like, take that order. 1, 2, 1, then 2, then 3, then 4. And then the next one is 1, 2, 4, 1. Then it goes 1, 3, 2, 4. There's a lexicographic ordering, but these are just a bunch of tuples. These are all your options for the permutations of those numbers. 1, 3, 4, 2 is next. And there's plenty more. But if you want to permute all n elements, so like this is 4 things, and we're permuting all of them, then there are n factorial ways of doing it. So there's 4 factorial ways of permuting these 4 numbers. But you can make that a bit more generalized. You can permute a certain number of those things from that original set. So PNR was the more general notation. That's trying to count all the R-sized tuples of coming from a set of n elements. So for example, I'm thinking and writing at the same time. P43, that would correspond to all the tuples that are of size 3 coming from this size 4 set, for example. So what's the first size 3 tuple? First it's 1, 2, 3, then it goes 1, 2, 4. So you're taking stuff from the original set, but you're only taking 3 things at once, and it's how many ways can you do that? 1, 2, 4, and all the orderings. 1, 3, 2, 1, 4, 2. There's again a lexicographic ordering there, and you can count that. It's just how many ways can you pick these 3 numbers. And so it ends up being, there's a calculation going on, but for example, this is going to be, well, you have 4 choices for the first thing, 3 choices for the second thing, and then 2 choices for the thing after that. It's almost a factorial, all right? So that's the idea. I guess technically it has the same size as 4 factorial, but that's what's going on, okay? So that's permutations, and that's how you count them. Next, we talked about combinations. In permutations, the order mattered, like 1 came before 2 here. These are tuples. But in combinations, we're trying to count subsets, where order does not matter. So maybe we have a set that is very similar, like we're trying to make all the subsets of this size 4 set, and we want all these size 2 subsets. So the question becomes, how many different ways are there to take 2 things out of this set and not count any what am I trying to say? Where the order does not matter. So like take 2 things, and it doesn't matter if it's 1, 2, or 2, 1, that's the same set. So like that counts as just one thing. 2, 1 is the same as that because they're sets. Then you have 1, 3. Then you have 1, 4. And then there is no 2, 1. If you're trying to do this in lexicographic order, there is no 2, 1 because you've already counted that one. 1, 2 is the same as 2, 1 as far as sets are concerned. Then you can do 2, 3, and I think that's the next one in lexicographic order, but of course there's more. And so combinations are counting subsets. You have this generalized notation CNR, which we tend to in math say N choose R instead, but I guess this is one way to write it with when you don't have that kind of fancy typesetting power. But we're counting combinations, and N in this notation is the size of the original set, where you're taking things out, and then R is the size of the subset that you'd like to make. So you'd like to make all the size R subsets of this original set of size N. So this is the size of the subset you're trying to make. And so the number of size 2 subsets from a size 4 set would be C42 or 4 choose 2. And the formula for that is going to be, well, it's how many ways are there to permute that divided by to permute those elements, divided by all the different possible interleavings and orderings of those elements. As we're like dividing by the number of permutations that would have counted to be the same thing, like the 1, 2, and the 2, 1. We're going to divide by a factorial to make sure that those don't overlap. So this simplifies to this n factorial over r factorial times n minus r factorial. But yeah, I like to think of it as like we're making permutations, like it's 1, 1, then 2. So like I have 4 choices for the first thing, 3 choices for the second thing as far as permutations go. But then I'm overcounting because I could arrange the size 2 set in any order, and I'll have repetition, so I need to divide by 2 factorial. So that becomes 4 times 3 over 2 times 1. That's how I think about it. But you can just use the formula on the final if you'd like. So that's combinations. Counting subsets. You can also talk about counting sets that have repetitions in them. So that's multi-sets, that's the name for that. So word scrambling was the way that we went there. So there is a fancy formula. You can check the slides for that, but I like to think of it as just filling in slots. So I think the example from the lecture was like all the different ways to permute the letters of the word Beyonce. And so we have repetition here. These E's are repeated. Their order doesn't matter if they are in the same spot, if that makes sense. So the way that you figure this out, the way that you can come up with the formula is you notice that you have 7 slots to fill. And the first thing you should do is pick where the E's should go. And it doesn't matter like this is the first E and this is the second E. It doesn't matter like you put the first E here and the second E here, because those are the same. Those are the same E's. It doesn't matter because maybe you put the first E here and the second E here. It shouldn't matter. There's no difference. You see that? Which one's first and which one's second? They're both E's. So you have these slots to fill in. 1, 2, 3, 4, 5, 6. Oh, sorry. There needs to be 7. Let me try and make room. Good enough. We need a 7th slot here. There we go. And so you got to pick where the E's go, and it could, it doesn't matter which E is first, like that could be either the first or the second E that you're placing there, and this could be the first or the second E that you're placing there. And the question is, how many different ways are there to place those 2 E's? Well, you have 7 slots to choose from, and you got to pick 2, and the order doesn't matter. That's where the combinations come into play. And then for every other character that there is no repetition for, like, all right, you got to pick a place for the B, you have 5 slots open now. So there's 5 times 5, and then for the next character for the Y, there's 4 slots open now, times 4, times 3, times 2. The rest is just a factorial. So that's how I think about it. So that's one thing that we care about. So that's like that's a multi-set. These E's count as duplicates, and we need to keep track of those. And then we talked about like choosing options from an infinite supply of things. So like picking 7 dogs from 5 different types of dogs, where you have an infinite amount of each different type. This is a very different kind of thing. So this has to do with making binary strings. Again, it has to do with multi-sets because It's not the case like I want 1 dog of type 1, 3 dogs of type 2, 2 dogs of type 3. See that's not equal to just the set 1, 2, 3. You've lost dogs at that point. So we have to use multi-sets where duplicates actually count and matter. And so the number of ways to select n objects from a set of m varieties is this fancy formula. And where it comes from is the idea that you can make a binary string that represents what things that I want from each type. So like the first thing comes first, and you just put a 1 for how many things of that type that you want, and then you have a 0 to separate. Now I'm ready to pick stuff for the second type. So you put as many 1s as you want to take stuff from the second type, and a 0 to indicate that I'm ready to start taking dogs of type 3. A 0 when you're done with type 3. That's just a separator. Another 1 for dogs of type 4, and maybe if I want 7 dogs, I've already picked 7. So type 5 would come after this 0, but I've run out of 1s to use. And so this formula comes from this idea that you can represent these choices as binary strings with 0s as separators between the varieties. And really what you're trying to do is you're trying to pick where the 0s go. You have a string of size, it has to be, this is n, plus there are types minus 1 separators that you need. So n plus m minus 1, and you're trying to pick the slots for just the 0s, and there are m minus 1 of those. That's how you do it. And so how many ways can you pick 7 dogs from 5 types? Where you can take as many as you want from each type, as long as it adds up to 7 in the end. That's going to be 7 plus 5 minus 1, choose 5 minus 1. Okay? So that's how that worked. It was all about the binary strings. That's how you encode this idea and how you can generate this formula if you ever forget it. So that is permutations with repetitions. Next comes binomial coefficients. That's when we have like a formula that looks like this. We have like, I don't know, 5a minus 7b cubed, and we want to know the coefficients. If you do this fancy FOIL expansion, you'll figure out that the coefficients come along for the ride, but we originally learned it without any coefficients. It's just like, all right, you have this thing, and you're taking it to the nth power, and so you're going to have a bunch of terms that look like this: a with a bunch of things, a bunch of a's, and then a bunch of b's, where it always adds up to these two exponents. They add up to n because that's what you're taking it to the power of, and the rule goes that the coefficient out in front of this is n choose k. That's how you do it. And then you can think about it in terms of b first. Like, it doesn't matter. N choose n minus k is going to be the same answer because it's a symmetric thing, the Pascal's triangle, symmetric. And so that comes from this idea, like a plus b cubed. Well, you can take 3 a's. It's trying to come up with a bunch of different possibilities. It's really counting sets. You can take 2 a's and a b, or you can take an a first, then a b, then another a. So like you have the same thing again. See that? Plus ... all the way to b 3 times, and you can bring these all together. But it's just it's counting every different possibility, and it's bringing together all these things where the order doesn't matter. So like those are considered equal, and we bring them together. And we can ask, what is the coefficient when there are 2 a's and 1 b? Well, the other option is like the b came first, then there were 2 a's. There's 3 of them. And you can get that from, like what goes here is, well, it's n choose k or n choose n minus k. And, all right, what is n? It's 3. What is k? That's what's next to the a. That's 2. So 3 choose 2 is what goes here. And that is going to be 3. Well, the number is 3. And how do you get that? It's 3 times 2 over 2 factorial. So over 2. And those go away, and that gives you your 3 like we thought there should be. And of course, you can calculate this using the Pascal's triangle. It's like 1, 1, 1, 1, 2, 1, and then it goes 1, 3, 3, 1. It is symmetric. And 3 choose 2 is, I think this is 3 choose 0, 1, 2, and 3. So this would be 3 choose 2, which is the same as 3 choose 1 anyway. You would have gotten it the same answer. So that's what's going on there. But that's the one that we circle, I think. So yeah, that's your binomial coefficients. That's how you calculate them. It is math secretly using combinations and counting them. Funny enough. All right. Next, we talked about algorithms. We were trying to generate all the permutations and all the combinations of certain elements of a set. And so we had these fancy algorithms, genlex permutations, which just kept calling next perm, and then genlex subsets, which kept calling next subset. I assume you're pretty acquainted with this by now since you implemented it, but let me show you like the quick and dirty way to do this on a test. Like, what is the essence of these algorithms? Let me show that to you. So, all right, let's say that we're trying to, let's do next perm first. So we're trying to permute the set 1, 2, 3, 4, all the different ways in lexicographic order. And of course, you start with a permutation. That's the thing in order. 1, 2, 3, 4. That's the first in lexicographic order. And then essentially, if you stare at this long enough, what is next perm doing with all these fancy indices and trying to do things and reversing and swapping? What it's doing is it's kind of like making a, it's computing a range as close to the right-hand side as it can. It's trying to say, it's asking the question, can I rearrange like the last two numbers and make a greater subtuple, like 3 and 4? Can I rearrange those in some way and make the next bigger subtuple out of 3 and 4? Well, yeah, I can swap that and get 4 and 3, and that's bigger. And so that must be the next permutation, 1, 2, 4, 3. And this is the game that you play. You just keep asking, like, all right, look at this. Can I rearrange the last two numbers and make the next bigger subtuple? No, 4, 3 is in reverse order. That's as big as it gets. Okay, in that case, widen your viewpoint and try and rearrange the last 3 numbers to make a bigger tuple. You got to make the next bigger one, so the smallest bigger tuple. So you got 1, 2, 4, 3. Can I rearrange those to make the next bigger tuple? Sure. I could put 3 first, and then it goes 1, 3. That's bigger than what was here. Or I guess here I could put 3 first, and that's bigger than 2 first. And then what's the next smaller one? It can't go 4, 2. That's big. I can go 2, 4. That's the next smaller one. You see that? So I've rearranged those 3 numbers to be the next smaller subtuple. And that's really all nextperm does. That's how it calculates things. This is how you program it, but this is how you should probably think about it if you haven't figured that out yet. So again, it's like, all right, can I rearrange? I need to make the next one. Can I rearrange these and make a next bigger tuple? Sure. 4, 2. 1, 3, 4, 2. That must be the next bigger permutation. All right, can I take these, make the next bigger permutation? No, they're already in reverse order. What about these? Ooh, yeah, I think so. I can make 4, 2, 3. 1, 4, 2, 3. That must be the next permutation. See that? And then, all right, can I rearrange these and make something bigger? Yeah. 1, 4, 3, 2. And you just keep playing this game, and then finally you get to like, all right, can I rearrange these and make something bigger? No. Can I rearrange these and make something bigger? No. All right, now you're forced to do the whole thing. Can I rearrange these and make something bigger? Yeah, I can put a 2 first instead of the 1. And then it's got to go, if I want this in order, it's got to go 1, 3, 4. Okay? And then, of course, there's plenty more after that. But that's how you think about it. It's like, take as little as you can on the right-hand side and like rearrange them to make the next bigger one, the next bigger one. Just keep on upping your window size until you can actually do that. And that's how you should think about permutations and generating them in lexicographic order. Let's talk about subsets. It's kind of similar. So let's say that we want to generate all of the 3 subsets of size 3 of the set 1, 2, 3, 4 again. And of course, the first subset, you have to figure that one out. That's given to you in the algorithm. That's going to be the 1, 2, 3. That's like the smallest subset that you can write. And then what next subset does when you give it this, it's trying to spit out the next bigger one. You need to find the rightmost element in your subset, in your current subset, that could be bigger. So, rightmost one. So here's this one. Could it be bigger? I'm trying to take things out of 1, 2, 3, 4. Yeah, it could have been 4. So that's the one that could be bigger. If it can be bigger, increase it to the next bigger thing. So 1, 2, 4, and then take everybody after it and increase it, like make it 1 bigger than the previous thing, 1 bigger than the previous thing that came before it. And there is nothing after the 4, so we're done there. So that's how you do that. That's how you calculate the next subset. And again, you start on the right-hand side and find the rightmost element that could be bigger. Now we want to generate the next subset after this one. Can we make a bigger element than 4? No, that is the largest thing in this set. All right. Then we go to 2. Can I make a bigger element than 2? Yeah, I can make 3. So it's got to go 1, 3, and then you start filling in every other slot. There's one more slot left with one more the previous thing. So it's got to be 4. 1, 3, 4. All right. So that's, I do +1 on that to calculate that. And then I can play this game all over again. All right, what's the next bigger subset than this one? All right, can this be bigger? No, it's already 4. Can this be bigger? No, it's already 3 and I've used 4. So there's no use rearranging it. I'm counting subsets. Like 1, 4, 3 doesn't count. Does that make sense? It's already there. So, all right, this one can't be bigger either. So that means we're forced to increase this 1 to 2. And so this becomes the number 2, and then we have 2 slots to fill, and you fill it by setting everybody after you to 1 plus the previous. So like this slot right here, it's going to be 1 plus the thing that came before it, so +1 to make the 3. And then this slot needs to be +1 from the thing that came before it, so I use the 3 to make 4. And that's how you build the next subset. And that is actually every subset, I think, that you can make out of those. And you can double check that by calculating how many 3 subsets are there of a size 4 set. It's 4 choose 3, which is going to be 4 times 3 times 2, like build all the permutations, and then divide by how many times you overcounted, which is 3 factorial, 3 times 2 times 1. I'll leave out the times 1, or I guess it's fine. And then these cancel, and so that means, yes, there are only 3 subsets of size 4 from an original set of size 4. So that's the process, or that's at least the trick that I noticed. So maybe you found something that works for you, but that's how I think about this kind of generation. If you have to do it on a test, I think that's probably easier to think about. If you had to code it, I do think that this is probably the easiest way to do it. You got to find these indices and do it in that order. This intuition, though, is the motivation for this code. Okay. So please yell at me if you have any questions about that. I think the last thing that we talked about in counting was the pigeonhole principle. And that was like, all right, the definition is a very easy one. It's like if you have 3 pigeonholes and 4 pigeons that you know are all in a hole, then in the best case, at a minimum, 2 pigeons are sharing a pigeonhole. Because you got 4 pigeons and 3 holes. Yeah? That. You are forced to have some pigeons overlapping. They could all be in the same pigeonhole, but at the very least, if they're spread out as much as possible, somebody's got to share with somebody else. That's all the pigeonhole principle is, and that is surprisingly powerful in proofs. So here's an example. A set of 8 numbers are selected from the set 1, 2, all the way to 13 and 14, so all the numbers from 1 to 14. Let's show that 2 of the selected numbers must sum to 15. All right, so here's a cute little proof. So what are all of the different ways that you could have chosen 8 numbers from this set? We can count that. Let's see. You're picking 8 numbers. There's a bunch of different ways to do that. And what are the sets, or what are the pairs of those that sum to 15? Because I just want 2 of those 8 to sum to 15. Well, there's one way to do it. You can pick 1 and 14 in any order. That's one way. You can pick 2 and 13. That's another way. 3 and 12. You could pick 4 and 11. You could pick 5 and 10. You can pick 6 and 9. Or you could pick 7 and 8. And so there are 3, 4, 5, 6, 7 ways that you could do this and pick numbers. And you are forced, I'm forcing you to pick a set of 8 numbers, right? So there are, here's the trick. You're forced to pick 8 numbers from this set. Like, all right, if you want to spread it out and like not give yourself a chance to add up to 15, it's like, all right, I'm not going to take the 14 if I take the 1. I'll take this one, and 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 this one. That's 7, and then I must take an 8th number. Do you see how every number is listed here, first of all? I must take somebody. So I'm forced to take a number somewhere. Maybe I take this one, and then I suddenly have a set of 2 numbers that sum to 15. That's the trick. That's the pigeonhole principle. So there are 7 subsets. 7 subsets that sum to 15. but we're picking 8 numbers. And so subsets of pairs of numbers. But we're picking 8 numbers, so you can't spread it out and avoid summing to 15. But we're picking 8 numbers. And so that's the proof. You're picking too many numbers to not end up with 2 that add to 15. That's how that works. So that's the pigeonhole principle, and that's one example of using it. It is very useful, especially in computer science, so that's why we learned about it. And so, all right, the final topic that we were talking about, the closest to the end of the semester, was probability. So let's go there, and that'll be it. So, all right, we got a lot of things, a lot of terms. So you're running a bunch of experiments, and those experiments result in outcomes, things that could happen. And you have a sample space of every possible outcome. So maybe your sample space is like you're rolling a single die, and your sample space is what is your outcome? What are all your outcomes? Well, it could land on a 1, a 2, a 3, a 4, a 5, or a 6, something like that. And an event is a subset of the sample space, like something that you would like to have happen. So maybe I want a low number. I want a 1, a 2, or a 3. And so you can make a subset of your sample space to talk about what you care about. Like I would like to talk about this event happening and calculate its probability. You can figure that out with a probability distribution, which is essentially a function that takes every outcome to a probability for that outcome. And so you have, like, for a die that's like not a cheating die, you have those 6 outcomes, 3, 4, 5, 6, and for each of them you have a 1/6 chance of getting that outcome, assuming it's a fair die. 4, 5, 6. Yeah, so it's just a flat line. That's a uniform distribution, but that's what a probability distribution in general is. It's like for every outcome, what is its probability? Just make a graph. And if you have a loaded die where it's different, you have a little weird looking graph like that. But the sum of your probability distribution must add to 1, because you can't have something over 100% chance happening, in the real world at least. So yeah, a die, a die or a pair of dice, whatever you want to talk about, that is a good example of a uniform distribution where the probability distribution for every outcome, or where every outcome has the same probability. You have a flat line. All right, that's cool, that's unbiased. And it's easy to calculate because you can just divide by the size of your sample space, the number of outcomes, and you get the probability. So like the chance that you land on a 5 is, well, 1 over, there's 6 possible outcomes, so 1 over 6. That's easy. Other probability distributions are hard to calculate. So that's that. And then you can talk about the probability of an entire event. It's like, what is the probability of this entire event happening? So getting a 1, 2, or a 3 somewhere from that event, well, because it's a uniform distribution, that's 3 over 6. 3 possibilities over 6 total. So you got a 50-50 chance of getting a low number like that. So that's probability terminology. Here's a silly example that I'll use for the next couple slides. So let's say that, take this as truth, the probability that it's hot outside, at least in Fresno in the summer, is like 0.5, like it's either sunny or nighttime. So that's one probability. And then the probability that it is hot outside given that you live in Fresno. So that's the idea, given that you live in Fresno. Assuming that, what is the probability that it's hot outside? That's what that means. Conditional probability, that means given, as you read it. Let's say that that's 99%, because Fresno's pretty hot. And then the probability that you live in Fresno, given anywhere else, let's just calculate that as the percentage chance that you are a human that lives in Fresno. So here's the population of Fresno, and here's the population of Earth, and let's say it's a random chance that you end up here. So this could be our probability that you live in Fresno. All right, so that's that big number. And let's talk a little bit more now about conditional probability. What is that? The conditional probability is, what's the probability of E given F? That is, assume that you're in a universe where F has happened. Like, you know that F has happened. How does that affect the probability of E? Because sometimes that changes if there's an overlap. So, for example, here is event E, all these different ways to make it happen. And then here's event F, all these different ways to make it happen. Maybe it's like that or something. And let's see here. The probability of E given F is this idea. It's, all right, you know that F has happened. What's the probability that E has happened? So if I know F has happened, like I know I'm somewhere here. I'm within one of these dots. And I'm now trying to ask, what's the probability of E? It's different because there are only a few different ways to make E happen. It's these ones specifically. So I'll take all these and divide by the total. You see that? So that's the new idea. So that's E intersect F over F. Probability of E intersect F over the probability of F. That's how you can calculate that. And so that is how you do it. All right? And you can calculate things. You can solve for this kind of stuff to determine independence. And so like what is the probability that it's hot outside intersected with you live in Fresno? You can use this because you have a conditional probability. I know that 0.99 is equal to probability of it's hot outside given you live in Fresno. So what do I have? Probability of it being hot outside given that you live in Fresno. Let's use H and F for that. I know that that's equal to, first of all, it's 0.99. But it's also equal to the probability that it's hot outside and I live in Fresno. So that intersection over the probability that I live in Fresno. And so I can calculate that, and I can multiply, like bring this over to this side. I can calculate this probability here, and I can determine independence. So what is that probability? Let's figure that out. It'll be fun. So what is the probability of H intersect F given my example here? I'm just going to Python for a second. So it's going to be 0.99 times the probability that you live in Fresno, dun, 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 which is apparently that I have calculated. 5.3 e to the 500,000-ish over almost 8 billion people on Earth. And it's a very small thing. It's a very small number. It's like 0.0000681. So it's a very small percentage, and that's how you can calculate that. And that actually proves that H and F, if it's hot outside and you live in Fresno, those are not independent events. It's more likely that it's hot if you live in Fresno. That's the whole point. So H and F are not independent events, and one way to notice that is that if the conditional probability doesn't give you any new information, like if the conditional probability of H given F is the same as just the normal probability of H, then it's an independent event. And it's definitely not, because the probability of it being hot is apparently this anywhere on Earth. So, yeah, at least in my made-up example. So another way to calculate that, or to notice that, is, well, if the probability of H given F is just equal to H, if it's an independent event, then another way to solve for that, if this is just going to end up being the probability of H, if it's independent, bringing the F to this side and leaving this on that side, that's the same as this. So the probability of their intersection is the same as just their multiplication of those probabilities. So there's a bunch of different ways to determine independence, but that's what it means. It means conditioning on one does not affect the final answer. So like you gain no new information by conditioning on whether or not you live in Fresno. You just get the same answer as the original probability of H, regardless of where you live. That would have been an independent event, but it's not, because it's hot here. So that's that. And then Bayes' rule is another way of talking about that or it's another way of using conditional probability to your advantage. It's how to flip. It's a way to flip things when you don't know everything, but you'd like another side. So like the probability of A given B, you can, if you use this formula and you split it up enough, you can solve for the other way. Probability of A given B in terms of the probability of B given A and some other probabilities. So if you know these things. So that's pretty nice. You see that? So if you want this side, but you only have this way, this flipped way, and then these original probabilities, if you have those, you can solve for the other flipped way. That's Bayes' rule, which is really nice. And you can also do this. You can solve for an, like if you don't know this thing to divide by, but you have the conditional probability of the event B given that A did not happen, so the opposite of A, the complement of A. that's also another way to solve that. And the probability of A not happening is just 1 minus the original probability of A. So you can easily derive that. But that's one way. So if you don't have P of B, there's a way to get that too. And so let's use Bayes' rule to calculate the probability that you live in Fresno given that it's hot outside. Because why not? So the probability that we live in Fresno given that it's hot outside with my made-up probabilities is going to be the flipped way, P of it's hot outside given that you live in Fresno, which we have, times the probability that you live in Fresno over the probability that it's hot outside, which is apparently, let's see here, we have 0.99 times, let's see here, times the probability that you live in Fresno, which is that, and then we have that all over P of H, which is the probability of whether or not it's hot outside, which we're going to assume is 0.5. So that's divided by 0.5, and that gives us this percentage. You can calculate a percentage by multiplying the final answer by 100. So it's 0.014%, given my made-up calculations. But maybe it's close enough to being accurate. Who knows? But there is a non-zero chance that you live in Fresno given that it's hot outside, but there are other places in the world. It's very uncommon to live in Fresno, so there are other ways for it to be hot outside and you be in another place. So kind of interesting. So it is unlikely that even though if it's hot outside, you probably still don't live in Fresno if we're taking a random sample of people on Earth. Because it's hot in other places too. So that's Bayes' rule with my made-up calculation. That's a way to flip a conditional probability. And yeah, the final stuff that we talked about was one of those things was random variables, and then I think there's one more thing after that. So yeah, random variables are just, you can think of it as like a function call. Like you call this function and it's using the random library, and it's picking some random choice every time you print it out and use it. So random variable x, it's a function from the sample space of an experiment to real numbers. So it's think of it as like a random variable that every time you print it, like the first time it gives you back a 1, the second time it gives you back a 3, it gives you back weird things, and it's random every time. But it's really a function from the sample space to numbers, and so we're like coming up with some quantification of every outcome. So let's say, I guess you can talk about this with spinners. That was our initial example. So you have a blue spinner and a red spinner. You can give a number for every outcome. Like this is a 3 and a 2. This was the outcome itself. It was the blue was 3 and the red was 2. Maybe what you care about though is like the sum of those numbers. So that, like the number that would be associated with this outcome might be 5, or maybe you want the product. So the number that's associated with this outcome would be 6, something like that. So yeah, here's an example. The range, by the way, of a random variable is just all the different numbers that it could take on, all the different number equivalents of each outcome. And so our running example can be the sum of 2 spinners. And it's always the case that a random variable has a number result. It could be a decimal number, but it's a number. Not a tuple, not anything else. So let's do sum of 2 spinners example. What are all the different outcomes if we're summing 2 spinners, where like the first thing is the blue one and then the second thing is the red one? Well, they could both land on 1, assuming they only have 3 options each. They could both land on 1. The first could land on 1, the second can land on 2. The first can land on 1, the second can land on 3. And then so on and so forth. 2, 1, 2, 2, 2, 3. I think you get the idea. 3, 1. 3, 2, 3, 3. Those are all the options. So that's your sample space. And then what is, let's make a random variable that calculates the sum of the 2 spinners. Right? So what are the different sums that we could make for this random variable? It's called the random variable y, maybe. So yeah, the sample space or the input space is the blue spinner value followed by the red spinner value, and these are all the different possibilities. But our random variable, let's call it y, is going to take on y of s. What's its range? It could take on the number 2, 3, 4, So it could be a 2, it could be a 3. There's a bunch of different ways to do it. It could be a 4, it could be a 5, could be a 6, but that's as big as it goes. 2 through 6. There are different ways to make other ones, so like it could have been 3, 2 or 2, 3 that made the 5, but the final value that's going to represent the sum of those things is 2 through 6. Those are the possible outcomes of the random variable, but they have different probabilities. And then you can come up with the distribution of like, how often is it going to be a 2? How often is this y random variable going to be a 2, assuming these spinners have random outcomes? How often is it going to be a 3, a 4, a 5, a 6? And you can do that by building a table. It could be like, all right, it could be a 2, it could be a 3, it could be a 4, it could be a 5, it could be a 6, and like we can count all the ways that that could happen. So like, what's the count? How many ways could it be a 2? Well, you got 1, 1, and that's pretty much it. There's only one way for it to be a 2. How many ways are there for it to be a 3? It could be a 1, 2, or a 2, 1. There's only 2 ways to make the answer, the sum for those spinners, a 3. So there's 2 ways there. What about 4? You have 2, 2, 1, 3, and 3, 1. So there's 3 ways to do that. What about 5? There's 3, 2, and 2, 3. So 2 ways, and then 6, 6 is just the 2 3s. There's only one way to do that. So it's kind of symmetric, which is cool. And then once you have the count, you can generate probabilities, assuming that every outcome is equally likely. What's the probability that you landed with, you ended up with your random variable having a 1 in it? Well, there's one way to do it, and 5, 6, 7, 8, 9 ways total. So it's a 1/9 chance that your random variable was a 1, that y was a 1 when you looked at it. Similarly, there's a 2/9 chance here, a 3/9 chance here, 2/9, 1/9 chance for all those things. Okay, so that's that. And then you can use this to think about what would you expect to see for your random variable on average. So let me copy this before I forget, because we're going to need it some more. Oops, not cut, but copy. So here's my little table. And now we can talk about the expectation of a random variable. Like, I want to know what in the world is the expected value of my random variable y here. What happens there? And so the way to calculate the expected value of a random variable is to just take a weighted sum. It's like for every outcome in the sample space, take the probability of that outcome times the value that you get back from the, what's it called? The value that you get back from your random variable when it's that particular outcome. Like it was a 1 and a 2, so like the outcome was 3. The random variable would have been 3. And then what's the probability that it was a 3? Things like that. You can also think about it this way, which is, I guess, technically the way that I said. This is like the probability that it was 1 then 3 times the outcome that you would get. Like it was a 4. Another way to calculate that is to make this weighted sum. Instead, it's just for every possible value of the random variable. Instead, take that value times the probability it was that value. And that's actually what we did in our table. This is like right here. This is the probability that our random variable had the value 3. We were calling our random variable y. That's the probability that y was 3, for example. And so we can use that to calculate the expected value of our random variable now. So what was the expected value of our y random variable for the sum of those two spinners? Well, it was a weighted sum. It was, well, it could have been a 2. The y random variable could have been 2 for that 1, 1 spinner. And there was one way to make it happen out of 9 possibilities. So it was a 1/9 chance. So it's 2 times 1/9. That's just a term in this summation. And then we're going to add that to, well, it could have been a 3, and the chance of it being a 3 was 2/9. 2/9. Or it could have been a 4 with a 3/9 chance. Or it could have been a 5 with a 2/9 chance. Or it could have been a 6 with a 1/9 chance. And the sum of that, if you go and you check, it's going to be 4. So the expected value that you can see over time, you expect to see about a 4 for your random variable. So that's usually going to be in the limit, the sum of those two spinners that you're spinning, which is cool. Let's see here. Next, we talked about the linearity of expectations. It's really cool that the expectation of a random variable is a linear kind of process where, like, if you want to know what's the expected sum of two separate random variables, you can just take their individual expectations that you probably already calculated and just add those together. That's equal. the same thing as if you have a random variable and you want to scale it by some constant. What's the value of the scaled random variable? What's the expected value of it? You can just take the original expectation and scale it, which is really cool. It's really nice. So, for example, what's the expected sum of 2 spinners? It really ends up being the number 2, because I'm scaling it by 2. It's 2 times the expected sum of a single spinner. Isn't that funny? So let's make a random variable z and watch it be the same. So let's define z to be the random variable for the random variable for the sum of one spinner, for the number on a spinner, essentially. For the number on just a single spinner. It's actually easier to calculate it like this. That's an I. So for the number on a single spinner, well, it's 2 n's. This does not look very good. But that's my word. And well, what could your spinner be? What's the outcome? What are your options? Well, it could be a 1, it could be a 2, or it could be 3 when you're just spinning a single spinner. And then what's the probability of each outcome? The probability. Well, 1/3 chance it was a 1, 1/3 chance it was a 2, 1/3 chance it was a 3. And so the expected value of z, if you do your weighted average here, it ends up being 2 because 2's in the middle and they each have a 1/3 chance. So the expected value of this z random variable is 2, and what I care about is what's the expected sum of 2 spinners. Well, what's that but just 1 spinner twice? So another way to calculate this idea that y had was, well, just take what's the expected value of the sum of 2 single spinners, which is the same as, you could either use this rule or this rule. It's the same as, these are z's, by the way. It's equal to the expected value of 2 times z, either way works, which is just 2 times the expected value of z itself, which is 4. That's another way to calculate the same thing. It's kind of cool. So that's linearity of expectations for you. It makes your life easier. Like, you didn't have to actually build this table. You could have just done it for a single spinner if what you cared about was the expected value. So that's pretty cool. It's like a weighted average. And then, yeah, let's see here. We have, at the very last thing that we talked about, we had our Bernoulli trials. All right. And so a Bernoulli trials is it's a special kind of experiment that you're running where you have only 2 possible outcomes, and you call those outcomes success and failure. So you either succeed or you fail. And a good example of that is like flipping a coin and like saying that heads is success and tails is failure. We usually care about counting all the ways that this could happen, calculating probabilities, talking about the distribution of all the different successes. So let's say that we make a bunch of independent Bernoulli trials, like we flip a coin and no previous coin flip has influence on the next coin flip, so it's independent. This leads to what's called a binomial distribution. All right. So the way that we can calculate that, what's the probability of exactly k successes in a sequence of n Bernoulli trials, so like n coin flips, where the probability of success is p and the probability of failure is called q, but that's just the opposite of p, so 1 minus p. The answer is n choose k times p to the k times q to the n minus k. So that's what's going on there. And this choosing happens because, like, let's say I'm trying to calculate the probability of rolling exactly 2 heads, or flipping exactly 2 heads when I flip a coin maybe 3 times. So I could get 2 heads immediately and then a tail. Or what are other ways to get 2 heads? Well, I could have a tail first, then 2 heads, or I could have heads, then tails, then heads, and I think that's everybody. So that's where this comes from. There's a bunch of different ways to pick where the heads happen. They could come in any order as long as you get 2 of them. So that's kind of what you're doing there and why this comes into play, right? And so exactly k successes and n trials. Probability of success is p, and then q can be calculated from p. Okay, so here's an example of that. Let's calculate the probability of getting exactly 3 1s after rolling a die 6 times. So you really want the low numbers. Maybe that wins your game. So what is your success event? Well, that's only when you get a 1. Do you succeed? What's your failure event? Well, that's every other number on the die. That's 2, 3, 4, 5, and 6. So Success is not in your favor, but let's calculate this. So the probability of success, P, is 1 over 6, right? Because you just want the 1. The probability of failure, Q, is 5 over 6. There's 5 options for not getting a 1, okay? And so what's the probability of getting exactly 3 1s in some order after rolling a die exactly 6 times? It's going to be, well, all right, we have 6 rolls and 3 successes. So it's going to be 6 choose 3 times, well, we had 3 successes, 3 1s, and then there were 3 more rolls left, and so we must have failed then 3 other times, and these could have come in any order. So it's 6 choose 3, and all right, let's calculate this. This is going to be 6 times 5 times 4 over 3 factorial, so over 3 times 2 times 1, nobody cancels, times 1/6 to the 3rd power times 5/6 to the 3rd power. So that's that. And let's see if we can calculate that. We have 6 times 5 times 4 over 3 times 2 times 1, all of that, times 1/6 to the 3rd power times 5/6 to the 3rd power. That is 0.54-ish. Oops, 0.054, sorry. 0.054. Let's see if I can move all this at once. Oh, I got lucky, nice. So that's 0.054. So 5-ish% chance that that actually happens, which is not too tiny. I guess it's definitely possible if you keep trying. So that's how you calculate that. That is an example of a bunch of Bernoulli trials calculating using the binomial distribution, a certain number of successes in a sequence of independent Bernoulli trials. And so I think that leads us to the end. That is all of the review that I wanted to talk about. So please use the rest of your time to study. Yell at me if you have any questions, but that's it. You've made it to the end of class. So thank you for your attention and putting up with me, and good luck on the final. So I'll see you during one of my office hours, maybe, if you choose to take it then. Otherwise, I will see you potentially in a future semester. So good luck with everything, and I will see you later.